So good afternoon all. So today we will solve the problem based on the chemical reaction equilibriums. I hope so you have gone through the week 12 lectures which are available on the importance. So we will solve the problem based on the reaction coordinate, then multi-reaction stoichiometry, then then the standard Gibbs energy change and the equilibrium constant and effect of temperature on the equilibrium constants. So starting from the MCQ one, working. So starting from the MCQ one, question one is the extent of reaction is option are given different for reactant and products, dimensionless, dependent on the stoichiometric coefficient, all the above. Basically, the extent of reaction is the same for the all the elements. This is not a. It is a the unit of the extent of reaction moles, and C is the dependent on the stoichiometric coefficient. C is the right ones. So equal to dni by vi. This is the stoichiometric coefficient. Ni in final moles of final moles divided by final moles minus initial moles divided by stoichiometric coefficient. This is the extent of reaction. It is dependent on the stoichiometric coefficient. Question to the equilibrium constant for chemical reaction depend on. Can someone tell the answer of this one? Equal to delta G. So equilibrium constant is depend on the temperature only. Now question 3 for reversible exothermic gas phase reaction A plus B gives C. The equilibrium conversion will increase with option are given increase in increase pressures and increase in temperature, and B decrease in pressure and increase temperature. So before going to the option, we say products summation of I equal to B stoichiometric coefficient. This is the product notations. Like for example, phi is equal to 1 to 5. Here is the I. So 1 into 2 into 3 into 4 significance of this sign means product notation. So exothermic So here total stoichiometric coefficient equal to -1. Here is the reactant of A -1 for B plus C. Sorry, it's a minus, right? So here total stoichiometric coefficient is negative, so it get positive, right? So it get positive. So it means the pressure is increased, right? And decrease in temperatures because here so here so it means temperature decrease, right? So here equilibrium conversion will increase. The option is C, means the equilibrium conversion will increase with in the increase in pressure and decrease in temperature for the exothermic reaction, right? All of you got this? Now question coming to the question number 4. For exothermic reversible reaction, which one of the following correctly describe the dependence of the equilibrium constant K with the temperature and pressures? Option are given. K is independent of T and P. K increase with increased T and P. K increase with T and decrease with P. And K decrease with increased T and independent of P. We know the relation K by K1 delta H R 1 by T 1 by T1, right? So for exothermic reaction, delta H is a negative. Hence, with increasing temperature, K decrease for exothermic reaction. And for endothermic reaction, delta H is a positive. So K is increased with increasing temperatures. So for the exothermic, K is decreased with increased temperatures, and it is independent of the pressures. All have got clear? If anybody anybody didn't get clear, please ask. Question 5. A gaseous system contains H2, I2 and HI which participate in the gas phase reaction. Twice HI gives H2 plus I2. This is a irreversible reaction. At a state of reaction equilibrium, the number of thermodynamic degree of freedoms. So here given a number of component 3 is equal to 3 and phase is 1, right? Now here is a one independent reactions. So that denoted by 1. So number of degree of freedom equal to C minus P plus 2 minus 1. Sorry, this is the R. This is the number of independent reactions. So put all the value in these equations. 3 minus 1 plus 2 minus 1, right? So 3. So degree of freedom F is equal to 3. That's the temperature, pressure and mole fraction. Question number 6, it is similar to the question 5. The reaction A gives to R plus H is allowed to reach equilibrium condition in atomic level. At equilibrium, there are the two phases. One pure liquid phase of A and other vapor phase A. R and yes. Initially, A alone is present. The number of degree of freedom are. So here same formula. F is equal to C minus P plus 2 plus R. R a number of independent. So here is a 1. Here number of component 3 and phases 2. 3 minus 2 plus 2 minus 1. So here. All of you got clear? Am I audible to all or not? Coming to the question number 7, match the following. Here a group 1 and a group 2. So here the given the equations. They have to match. So dg divided by dni dp in j not equal to the I. That's the chemical potentials, right? And dg divided by dni at s v and in j not equal to I. So this equation does not have any significance. And exponential minus delta G reaction divided by RT, the reaction equilibrium constants, and summation in I d mu I at temperature and pressure. That's the Gibbs tube equation. So see the answer of. And RNA case equation K is equal to K to E RT. This is the activation energy. This is the constant, the exponential constant. Question 8, enthalpy of formation at 298 Kelvin, delta HF denoted by formations of CO2 and PbO are minus 393 kilojoule per mole and minus 220 kilojoule per mole respectively. The enthalpy changes for the reaction twice PbO plus C gives 2 PbCO2. So enthalpy of formation given for PbO and CO2. Yeah. So I have to calculate enthalpy change for the reactions. Calculate the change of enthalpy for these reactions. Delta H for a reaction, delta H product minus reactant. Right. Here is there here for toy 2 pb 0 plus CO2 given 3. For PBO twice into minus 220 plus 0. So 47 kilojoule. All of you getting? Now moving to the question number 9. At a given temperature K1, K2 and K3 are the equivalent constant for the following reactions 1, 2, 3 respectively. Chemical reaction are given here. Then K1 and K2 and K3 are related as. I'll have to try how do you solve this one. So this is a chemical reaction number 1, 2 and 3. Suppose we add equation 1 and 2 here. So CH4 then CO get cancels. Here is 2 twice is 2 plus CO2 plus 3 plus 1 4, right? This is Bala's equation. So when we add 1 and 2 gives the equation number 3, right? So delta G 3, so delta G1 plus delta G2, which is equal to RT ln K3 equal to minus RT ln K1 plus RT ln K2, right? This get cancels. ln K3 ln K1 plus ln K2 ln K3 into ln K1 into K2. K3 is equal to K1 into K2. Check the options. So A is the right answer. All of you got clear? Question 10. The chemical reaction givens twice Cu plus 0.5 O2 gives CuO, and it's a reversible reaction. The molar free energy change at 1300 Kelvin for the transformation of solid Cu to less Cu will be. We have to calculate delta G, right? We have to here. So here really given the relation for the delta G and reaction 1 and 2. This is the equation 1 and equation 2, or reaction number 1 and reaction 2. Now here is a transformation solid Cu to liquid Cu. It means that we have to minus 2, sorry, means we have to proceed equation 1 minus equation 2, right? So it cancels, it cancels. So this U, yes, twice U, L, right? So for this reaction, we have to calculate the molar free energy change at the 1300 Kelvin, right? So similarly, equation 1, equation 2. This is a reaction 1 and reaction 2. Now the 1 minus 2, we have to, means equation 1 minus equation 2, then you will get equations delta G 26 100 minus 19.24 T, right? So put the value of this 1300 in this equation, you will get delta G 1088 joules. For the 2 moles, this is for the 2 moles per delta G per mole equal to 544 joule per mole, right? Option C is right. Now question number 11, at a standard conditions N2 plus twice O2 gives twice NO2 and delta G given, and NO plus 1 by 2 O2 gives NO2, reversible reaction, and delta G given. So this is a chemical reaction number 1 and reaction number 2. The standard free energy of formation of NO in kilojoule per mole. So in a given the delta G for reaction 1 and reaction 2, so we have to calculate standard the free energy for formation NO. So here is a in product no is a NO. So I have to make a changes. So in a reaction number 1, so multiply by 1 by 2, and reaction 2 exchange reactant and product each other. Equation 1 multiply 1 by 2 1 by 2 n2 plus O2 NO2, right? And reaction, and the reaction to exchange reactant and product each other's. NO2 NO plus 1 by 2 O2. Now the formation of NO, right? Similarly for this delta G, here 1 by 2 and it exchange means it get a positive, right? It's a 50 kilojoule per mole. Now add a reaction, which is reaction number 3 and 4. Now add reaction 3 and 4. So you need to get cancels by 2 N2 plus half O2 by NO, right? So add delta G one reaction 1 and 2, sorry for reaction 3 and 4. So delta G equal to 50 plus 35, so 85 kilojoule per mole. Answer is the C. All have got clear? Now question number 12. A vessel initially contains not moles of water vapor only. If decomposition of water vapors occur according to the reaction, H2O use H2 plus 0.5 O2. The fractional decomposition of water vapor in terms of reaction coordinates is equal to. We have to derive the expressions, right? As you know, mole fraction is equal to Ni total moles equal to Ni of species initial is stoichiometric coefficient into reaction coordinate plus initially total moles plus total stoichiometric coefficients into extent of reaction rate. So total mole at initials is not given, right? And stoichiometric coefficient for the reactions -1 for H2O plus 1 for H2 and plus 1 by 2 for O2. No? 1 by 2, right? So here ask for the fractional decomposition of water. How to calculate? So NO water initially minus N H2O moles of water and initially water presents. Right. Now I have to calculate for water, moles of water after reacting. So initially presents in not, right. So yeah, in a reactant, so that's negatives, and active stoichiometric coefficient is 1. Now put these equations in not reaction equal to 5 in fractional decomposition of water vapors. Right. All of you got clear? Question number 13. Are the systems in which of the following reaction occur? CH4 plus H2O gives C1 3H2O. Assume there are present initially 2 moles of CH4, 1 mole of H2O and 1 mole of CO and 4 mole of H2O. For the reaction coordinate equal to 0.5. Right. The mole fraction is maximum for and minimum for A. So initially, total mole presence is not equal to 2 plus 1 plus 1 plus 4 equal to 8. Right. And total stoichiometric coefficient 1 plus 1 minus 1 minus 1 plus 1 minus 3 equal to 3 plus 3 4 minus 2 2. Right. Now to derive the mole fraction for a species, y is equal to n I is equal to plus vi to NO plus stoichiometric coefficient into reaction coordinate, right? So YCH4. So initially CH4 is the 2 moles, right? And stoichiometric coefficients minus 1, which means right, minus 1 and reaction coordinate. And initially total moles was initially moles 8 mole. 8 and stoichiometric coefficient 2, so it's a positive. Similarly for the EH2O, 1 minus 8 plus twice HCO, 1, so stoichiometric coefficient per product get positives. Reaction coordinate twice y is to initially moles 4 plus ice, here is a stoichiometric coefficient 3 and it is in product, so it is positive and moles. So here reaction coordinate value given by you put in all equations. Zero point 116 and the H2O 0.055 and CO 0.16 and H2 0.61. So the mole fraction is maximum for S2 and minimum for the waters. So option D is the match. All of you got clear? Question number 14. A gas mixture containing 3 moles of CO2, 5 moles of H2 and 1 mole water is undergoing the following reaction. CO2 plus H2 gives methanol plus waters and CO2 plus H2 gives monoxide and waters. Develop the expression for the mole fraction of species in terms of the external reactions. These are multiple reactions. So one, reaction number 1 and then reaction number 2. Right. So for multiple reactions, Ni equal to initially moles of species I plus summation J equal to Vi J to reaction coordinate J. Here Vij denote the stoichiometric number of species I in a J reaction. Right. And to calculate mole fraction of Y is equal to NiO plus summation G Vij initially moles presence plus summation J Vij reaction coordinate. Right. Now the stoichiometric numbers Vij. So here I choose CO2 S2 the species CS3OH H2O and CO. And J is a reactions. Here 2 reaction. Here is a totals. So for this is the tables for the stoichiometric number. Here CO2 is a -1, right? And S2 -3. CO1 and H2 is 1 0. And for second reactions, the CO2 minus 1 H2 minus 1 0 H2 1 1. Here is the Vg totals, the minus 2. So minus 1 minus 3 minus 4 and plus 2, so minus 2, and this gets a 0. Now the total moles initially present, n 0 is equal to 3 into 5 into 1, that's 9. Right. Now total moles after the reacting, equal to these terms, n naught plus summation V T to extent of reaction. So here initial moles 9, right, and the totals coefficient minus 2, so here is a minus sign, 2, 1, right, because here is a 0, right. Now calculate for all species for CO2 3 minus reaction extent for 1 minus 2 9 minus 2 y is 2 5 minus 3 2 9 2 r is 2 1 plus reaction extent for 1 reaction extent for the reaction 1 plus 2 9 2 for CO2, sorry, for CO extent for reaction 2 divided by 9 minus for CS methanol minus the reaction. So these are the derived expression for mole fraction of species in terms of the extent of the reaction. All have got clear. So this is the expression for the multiple reactions. Moving to the question number 15. The water gas shift reactions. Carbon monoxide plus waters gives CO2 and H2. It's carried out at 1100 Kelvin and 1 bar with 1 mole of H2O vapors and 1 mole of CO present initially. At 1100 Kelvin, the equilibrium constant of the reaction is found to be 1. This is the key. If the reaction mixture behave as an ideal gas, the fraction of steam that reacts is. The fraction of this, so I have to calculate the fraction of the steams. That's the react. So initially moles 1 plus 1 2 and stoichiometric coefficients, K is given, temperature given, pressure given. So minus 1 get 0, minus 1 minus 1 plus 1 equal to 0, right? Now to calculate the reaction extent of reactions, there is one relations K into P stoichiometric coefficient superscript 2 product summations, product notations into yi vi, right? So K is given, P is given, stoichiometric coefficient is now calculated. So now first derive the expression for the mole fraction of each species. So y GS2O equal to is the initially 1 moles water vapor and stoichiometric coefficient in here water vapor in a reactor, so that's a negative into reaction coordinates into twice and total stoichiometric coefficient is 0, so it's a 2, so 1 by right. Y H2O sorry YCO same for YCO2, right. So initials moles of CO2 is 0, right? Reaction coordinate divided by 2 and for Y is 2 equal to 0. Now put this equation in this relations. So here total stoichiometric coefficient 0, this gets a 0, so P is it's a 1 equal to Y CO2 into mole fraction of S2O, sorry S2 divided by mole fraction of CO into mole fraction of S2O, right? So mole fraction of product divided by mole fraction of reactant, right? So put these mole fractions expression in these equations, you get 1, and here K is a 1, so right. So So fraction of steam that reacts is 0.5. Option C is the right one. Right. Now moving to the question number 16. The water gas shift reactions CO plus H2 gives CO2 and H2O. Is carried out at 1100 Kelvin and 1 bar with 1 mole of H2 vapors and 1 mole of CO present initially. At 1100 Kelvin, equilibrium constant of reaction is found to be 1. Assuming ideal gas behavior, the reaction mixture, the fraction of steam that reacts is found to be 0.5. If the initial reactant mixture contains 2 mole of N2 along with 1 mole of H2O vapor and 1 mole of CO, the fraction of steam that reacts. So this statement is same, almost similar to the question number 15, but here is a extra part added here. 2 moles of N2 along with 1 mole of water vapors and 1 mole of CO. So here N2 does not take part in the reaction and it serves only as a dilutant. So it does increase the initial number of moles from 2 to 4. Then not 4. And mole fraction reduced by the factor 2. Right. So here ask for the fraction of steam that reacts it. So it's similar to the 0.5. Right. Because for mole fraction of H2O equal to 1 by 4. So the 4 get cancelled. So you will get relation similar 1 minus external reaction square external reaction square. So pi is equal to 1 by 2. Option is a getting or not. Yes, students, are you there? Question number 17. The reduction of APO with CO in a co-current flow is given by the following equations. The APO plus CO use AP S plus CO2 and gives energy given at this temperatures. The ratio of PO, this is a partial pressure of CO and divided by partial pressure of CO2 for this reaction at this temperatures. Option are given. Can anybody tell how to solve this one? So in this question given delta G given, temperature given, right? So we can calculate the equilibrium constant. Is my slide visible? So in this equation given delta G and temperatures, so we can calculate equilibrium constant using this equation. Delta G is equal to minus RT LA K. Delta G given R is equal to as constant 8.31, R is equal to 8.314 joule per mole Kelvin. So you get K value here. K is equal to 0.435. Now equilibrium constant is related to the fugacity of the components. So K is equal to issue K equal to product notations to Fi into this relation. Fugacity of solid is a 1, right? Y CO 2 into pressures HCO into pressures. So mole fraction into total pressure is a partial pressures. So PCO 2 equal to K, right? So we calculate the K equal to 0.435. In the question at ratio of PuCO2 means partial pressure of CO divided by partial pressure of CO2. So PCO PCO2 equal to 0.435 equal to 2.3. All of you getting this one? Question number 18. The vapor phase dihydration of C2H42 ethanol by the following reaction. C2 ethane plus water gives some ethanol. Attains the equilibrium at 400 Kelvin and 3 bars. The standard Gibbs free energy change of reaction at this condition is delta G equal to 4000 joules per mole. Are 2 moles of equilibrium feed of ethylene and steams. Sorry, here is ethylene. The equation in terms of the extent of reaction at equilibrium. So we have to derive. Option are given. Right. Equal to Yi into Vi equal to minus V into K. Here is a P by P naught V. So P at the pressure at standard states at 298, it's 1 bar. Where is a 1, so it not a significance on these terms, so that's only the P. So now calculate the first equilibrium constant using this equations delta G equal to minus RT ln K. So T here temperature given 400 Kelvin, R gas constant, delta G given. So calculate the K value. So K is a 0.3, right? Now for mole fraction, so initially 2 moles, so and the stoichiometric coefficient for these reactions is -1, right? -1 -1 plus 1 equal to the -1. Okay, calculate the mole fractions for each species. YC2H4. So initially 1 moles of C2H4 and reactant Z negative stoichiometric coefficients to extent of reaction. And initially total moles 2 and at stoichiometric coefficient total for this reaction is -1. Minus H2O equal to same, and for ethanol C2H5. So initial moles not present. Now here stoichiometric is positive for products. Is the total moles. Now here is a negative get cancels, and this is positive. So P into K equal to YC2H5OH and mole fraction of ethanol divided by mole fraction of C2H4 into YS2O. K equal to C2H5OH YC2H4 into mole fraction of the water. So P is a 3 and the equilibrium constant calculated 0.3. So 2 square, right? 1 by 3. This is a 0.9. One minus 2 minus to 0.9 equal to 0. We check the options. So this is the correct. All of you got clear? Now moving to the question number 19. Calculate the fraction of pure ethane that would dehydrogenated at 750 Kelvin and 5 atmosphere if the following reaction goes to equilibrium. C2H6 plus C2H4 plus H2. So delta G for a reaction at 750 Kelvin, 42.576 kilojoule. Assume the gas pure. Here we have to calculate a fraction of pure ethane. So delta G given, temperature given, pressure given. Okay. So initially calculate the K value, equilibrium constant, using this relation minus RT ln K. So K is equal to 0.9932, right? And here consider the 1 moles of ethane station initially, so not equal to 1. And stoichiometric coefficient -1 plus -1 plus 1 for C2H4 plus 1 for 2 minus 3 to 1. So I have to calculate the mole fraction for the ethanes. Y C2H6 right here. Now K is equal to P mole fraction of C2H4 into mole fraction of H2 divided by mole fraction of C2H6, right? So here is a V is equal to 1, this is the -1. So we can take P here, this same into P, right? Now calculate the expression for the mole fraction of each species C2H6. So initially 1 moles, initially presents 1 moles. So C2 is the reactant, so stoichiometric coefficient is minus, and reaction extends, and totals moles were 1, and here is the positive signs. So Y C2H6 C4. So initially moles of 0 of C2H4 0. So reaction extent divided by 1 plus total mole for CH2. Now this expressions of mole fraction put in these equations. So K is a 0.9932 into 1 by 3. It's the same one. So here 1 by 5 1 by reaction extent, right, into P is a high atmosphere, and all these expressions get phi is equal to 0.40. In the question asks the fraction of pure methanes. So this one to calculate. So Y2 H4 equal to 0.4285. I need to check it. It's a 0.42. All of you got clear? So moving to the question 20. For a gas phase, the cracking reaction A gives B plus C at 300 degrees Celsius. The Gibbs free energy of the reaction at the temperature is delta G is equal to minus 2750 joule per mole. The pressure is 1 bar and gas phase can be assumed to be ideal. The universal gas constant R equal to 8.314 joule per mole into Kelvin. The fractional molar conversion of A at equilibrium. So we have to calculate the fractional molar conversion of A at equilibrium, right? So in this questions, we have to use same concept as the previous questions. So first delta G given, temperature, pressure given. So calculate the first key equilibrium constant equal to xv plus delta G by RT. Put the value and get k is equal to 1.78810, right? Equal to I P naught into K. So here total moles of A is the A is equal to 1 mole. It's a PMBC. So A naught equal to 1, right? This P naught equal to 180. 1 bar. It's only P. So X is a fractional molar conversion. So this is a species A, B, C. So stoichiometric coefficient -1, 1, 1, right? The totals. initial moles 1 0 0, so P is equal to 1 and 2 1, right? At equilibrium, so 1 minus x, right? The x and totals 1 plus x, right? And mole fraction 1 minus x by total moles 1 plus x 1 plus x, right? Now put the equations 1.7810 equal to yb into yc by ya. X 1 plus x, x 1 plus x 1 minus x plus 1 plus x, right? And p right. Calculate that. What is the value of p? P is a 1 bar. So is equal to 0.8. So fractional molar conversion of at equilibrium is 0.8. So option D is the right. Clear or not? So moving to the last questions of these questions. The standard Gibbs free energy change, the enthalpy change at 25 degrees Celsius for the liquid phase reaction. Okay. So CH3COOH plus C2H4OH gives C2COO C2H5 plus H2 are given as delta G at 298 minus 465 joule per mole and delta H at 298 equal to minus 3640 joule per mole. If the solution is ideal and enthalpy change is assumed to be the constant, the equilibrium constant at 95 degrees Celsius. So you have to calculate the K value at 95 degrees Celsius. So delta G given, delta H given, and the standard Gibbs free energy change and enthalpy at 25 degrees Celsius. Right. So there are two relations, K is equal to xp exponential delta G RT in ln K K1 delta G R 1 by T and 1 by T1, right? First calculate the K value at 25 degrees Celsius. Delta G given are 8.314 and T is 25. So convert into the Kelvin. So get K is equal to 6.5 326. equation. Now put the value A is equal to here, and delta is at 290 degrees Celsius, this one value, and 1 by T means 90, T means 95, convert into the Kelvin. K ln 6.5326 to K1 equal to, it gets value to 3640 to 8.314. 25 plus 273.2 minus 125 plus 273.2. Right. So K1 at 95 degrees Celsius equal to 4.94. Right. Option B is right. I hope you got clear. Okay. So I cover all the question based on the chemical reaction equilibriums. So if you have any doubt, please ask, because this is the last sessions. Okay, thank you all, and all the best for the final exams.